This is the most important question, that how we can estimate our parameters if we have the case of perfect multicollinearity. In the case of perfect multicollinearity, regression coefficients remain indeterminate and their standard errors are infinite, as we had already discussed. That if you are dealing with the case of perfect multicollinearity, so you have a regression model, and in your regression model, suppose your two variables are perfectly linearly dependent on each other. So what will be the result? The result will be that you cannot determine your regression coefficients. You cannot get the value of beta 2 and beta 3. And similarly, your standard errors will be infinite. For example, we have this regression model, yi is equal to beta 2. Actually, this regression model is in deviation form. When you will read the book, you will find that how we can formulate this model. But very simply, this is beta 2. You can calculate beta 2 from this expression, and similarly you can calculate beta 3 from this expression. And we are saying that suppose x3 is equal to lambda x2. x3 is equal to lambda x2. It means there is a perfect linear relationship. If this is the case, so if this is the case, I mean to say, if the relationship between x3 and x2 is a perfect linear one, so substitute this expression or this relationship in the equation 7.4.7. What you will get? You will get 0 on the numerator as well as 0 on the denominator side of the given expression. This is indeterminate. We cannot determine. It means that if we have the case of perfect linear relationship, we cannot determine the regression coefficients. Now, what about beta 3? This is the slope coefficient of x3 variable. Similarly, if you substitute this relationship in 7.4.8 to calculate the value of beta 3, again you will get this answer. So we can say that if we have the case of perfect multicollinearity, we cannot determine our population parameters. We cannot estimate beta 2, beta 3, beta 4, and so on. The question is, why we are getting this result? Why we are getting an indeterminate expression for beta 2 and beta 3? Very simply, you have beta 2. What do we mean by beta 2? Actually, beta 2 gives you the rate of change in the average value of y as x2 changes by a single unit, holding x3 constant. Suppose we have a regression model, y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus ui. Actually, you know beta 2 represents the slope coefficient of x2 variable. It means that if we change x2 by a single unit, by 1 unit, on the average, how much change will occur in our dependent variable, which is generally known as slope of a regression line. If you are changing x2 by a single unit and your x3 is constant, so how much change in y will occur? But if you have the case of perfect multicollinearity, the case which we are discussing, there is no way x3 can be kept constant, because when we are interpreting beta 2, we are saying that x3 is constant, and if we change x2 by a single unit, on average this much amount of change will occur in our dependent variable. Okay, this is clear. But the main issue is that if you have the case of perfect multicollinearity, you cannot keep x3 as constant, because x2 and x3 are perfectly collinear. It means that if you are changing x2, it means you are also changing x3 by the factor lambda. We are saying that x2 x3 is equal to 5x2. Suppose we have a regression model. Y is equal to beta 1 plus beta 2 x2 plus beta 3 x3. This is a multiple regression model where we have two independent variables x2 and x3. Now I am saying that if we change beta 2, the slope coefficient of x2 variable, if we change if we change x2 by a single number, a single unit, if we change the value of x2 by 1 unit, by keeping x3 as constant, so on average the value of y will change by any amount. Suppose you have
Yes, sir. Yes, sir.
three variables. One is consumption, your consumption expenditures, those amount which you are spending on purchasing food. You have consumption expenditure. This is your dependent variable. And you have two independent variables. One is your income and second one is your wealth. You have two independent variables, income and wealth, and your dependent is consumption. It means that your consumption expenditures are dependent on your level of income and your wealth. Now, when you will design your model, you will write y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus ui. So your beta 2 will represent the slope coefficient of your income, and beta 3 will represent the slope coefficient of your wealth. If we are changing beta 2, the coefficient of x2 variable, I mean to say the coefficient of the income variable, by 1 unit. So how we will interpret? We are saying that if we change our x2 variable, mean income, I mean to say that if there is a 1 unit change in income, by keeping your wealth as constant, on the average this much amount of occur will occur in your y variable, maybe 0.5 or something. Similarly, when we are interpreting beta 3, we can say that by keeping x2 constant, now we are keeping the income level of a consumer constant and we are changing his wealth. So we are saying that if there is a 1 unit change in wealth of a consumer by keeping x2 constant, so on average a certain amount of change will occur in the dependent variable. But when you have the case of perfect multicollinearity, you cannot keep any variable constant. This is the main issue. Why? Because they are perfectly linearly dependent. It means that if you are changing one variable, the second variable is also changing by a fixed number, by a factor of lambda, suppose. Then you are not able to know their separate influence of the dependent variable. As you know that your income is separately influencing your consumption and your wealth level is also separately influencing your consumption level. It means that you are separately interpreting or individually interpreting one variable by keeping the other variable is constant. But when you have the case of perfect multicollinearity, you can't do such kind of individual interpretations. You can't individually interpret one variable because you cannot keep constant the second variable. You are changing one variable, your second variable is also changing. If you want to know its mathematical manipulations, you can do it very simply. You can just need to substitute the expression as in equation 10.23. You will get suppose alpha, and you know that alpha is the combination of beta plus lambda b3. Now when you will run this regression, so the EView software will give you answer for alpha. This is a parameter. Now my question is that how you will interpret this value, because alpha is not, in this case it is a single value, but this value itself is the combination of two slope coefficients, beta 2 and beta 3. So in this case, you are not able to interpret beta 2 and beta 3. You cannot say if we change x2 by this much amount, so y will change by this much amount. No, you can't say, because alpha is not the slope of a single independent variable, but actually this value or this parameter is the combination of two other parameters or two other slope coefficients. That's why in the case of perfectly multicollinearity, you cannot access the influence of one variable on the dependent by keeping the second variable as constant. So what you will get? You will get an infinite number of solutions if you try to solve this equation. Although this is one equation where we have two unknowns. Look at equation 10.2.6. This is one equation where we have two unknowns. Although the value of lambda is given, you have two unknowns, beta 2 and beta 3. Lambda, although lambda is unknown, but its values are given. So that's why we are saying that we have two unknowns, beta 2 and beta 3. And if you are interested to calculate the value of alpha, you will find infinite solutions for the given values of alpha and beta. For example, you want to know the value of beta 2 and beta 3, where lambda is given and alpha is given. So you have the values of alpha and the values of lambda, and you are interested to know beta 2 and beta 3 values. You will find an infinite number of solutions. How? For example, if alpha is equal to 0.8, this is the alpha value, and lambda is equal to 2. You want to know the value of beta 2. Beta 2 is equal to 0.8 minus 2 beta 3. If you substitute beta 3, for example, 1, you will get a value of beta 2. If you substitute beta 2, for example, 2, then 3, then 4, it means that you are changing the value of beta 3 arbitrarily, and then you are getting the solution of beta 2. Then you are changing another beta 3, you will get another solution for beta 2. If you are trying to continuously by substituting different values for beta 2, you will get different values, sorry, for beta 3 you will get different values for beta 2. It means that you will never find a unique solution for beta 2. It means that if you have the case of perfect multicollinearity, and if you want to calculate the value for your parameter, suppose beta 2, you cannot get a unique solution. You will get as many solutions as possible by substituting different values for beta 2. So this is the main issue of the presence of multicollinearity, because in the case of perfect multicollinearity, the variance and standard errors of beta 2 and beta 3 individually are infinite. Now this was the value of beta 2 and beta 3. Now if you want to know the variance of beta 2, or if you are interested to know the standard error of beta 2, you will get an infinite number. For example, this is beta 2, and if you have the case of perfect multicollinearity, you cannot determine beta 2. But in this case, for example, where we have a stochastic error term, so estimation of the regression coefficients beta 2 and beta 3 may be possible if you have not a perfect linear relationship. The case of nearly multicollinearity means if you add the VI term, the stochastic disturbance term. So in this case, you can calculate beta 2 and beta 3. But again, if the value of VI, the stochastic disturbance term, is sufficiently small, for example, if this value is close to 0, like for example, if you are taking the value of VI 0.01, for example, a 0.001. So this equation will converge to the previous case where you cannot find the solution for beta 2. Look at this case. This is, by this way we can calculate beta 2. This is the expression for beta 2. But if your x2 and x3 variables are perfectly collinear, you cannot get this beta 2 value. It is indeterminate. Similarly, if your x2 and x3 are perfectly collinear, you cannot determine beta 3. But in this case, here we are using or adding v item. Look at equation 10.3.1. Now you are including this term. At the moment, we don't have the case of perfect multicollinearity because we are adding v item, the stochastic disturbance term. If you are adding this stochastic disturbance term, it means now you have the case of nearly perfect multicollinearity or near perfect multicollinearity. So if you want to estimate beta 2, now in this case you can estimate. And similarly, if you want to estimate beta 3, you can estimate because now you have near perfect multicollinearity case. So you can estimate beta 2 as well as beta 3. But again, the question is that if, what about if this value is small? If this value is sufficiently small, for example 0.0001, if this value is sufficiently small, and if this value is equal to 0, if this is sufficiently small means equal to 0 or near to 0, then again you are moving towards the case of perfect multicollinearity. So again you cannot determine beta 2 and beta 3, and your standard errors will be infinite. This is the simple data, x2 and x3, and we know that x2 and x3 are perfectly collinear. So if we want to estimate beta 2 or beta 3, in this case it is impossible. We cannot determine the slope coefficients or the regression coefficients. So what we will do, we are just adding v item, the stochastic disturbance term. We are adding this term to make this model or this relationship a nearly perfect. But my question is that if this value itself is very small, it means that again we are going back to this case. Like for example, this is 1050 and I'm getting x3, and if this value is 50.001, so what about x2 and x3? It means that in this case again we cannot determine. It means that there is nothing changed. We are going to the same case as the case of perfect multicollinearity.
Okay.
This is the case. It is very clear for you, the relationship between x2 and x3. If I am adding vi, suppose the vi value is suppose 12. So this new value will be x3 new value will be 62 because I am adding 12 to this value. So 50 plus 12 is equal to 62. Now look at this value has changed. If this value has changed by a large amount, it means that now there is no exact linear relationship between x star 3 and x2. It is very clear because I have added a large amount to x3. Now x star 3 is 62. But let me give you another example. If I am adding suppose 0.1 to x3 and I am getting the value, for example 50.1,
Okay.
So it means both the cases are very near to each other. Although I have added the stochastic value, but this value is sufficiently small. Objective of the discussion is that if we add vi by suppose 0.001, very small, if we are adding a very small value for vi, so you will get, if not the same answer, so a very near answer. Like for example, look at this. This is 50, and if I am adding 0.001, so I will get
001.
50.001. So what is the difference between 50 and 50.001?
Negligible, very small.
Very, very small. That's why I am saying that if the value of vi is very, very small or sufficiently small, or even if we can neglect this value, it means that we are going back towards the previous case, the case of perfect multicollinearity. This is beta 2 and beta 3. If x2 and x3 are perfectly linearly related with each other, it means we cannot estimate beta 2 and beta 3. Is it okay?
Yes, of course.
Okay, now what we are doing? We are actually just adding vi term to the same model. Then we can say that yes, now we can estimate beta 2 and beta 3 because we have added vi. But the whole summary of the discussion is that if the value of vi is sufficiently small, if this is very, very small value, it means in that case we will go back towards the previous case, and we cannot estimate the value of beta 2 and beta 3. It means that we are moving back towards the case of perfect multicollinearity. So what we need to do, we need to assign a big value for vi in order to avoid the perfect multicollinearity situation.